Hi, everyone. I want to report on some work in progress we have in the formal methods team in input-output. As a tribute to Conor McBride, I've split the talk in two. The first part is the one I've prepared, the second, the one that I will improvise. And that's the end of part one. So we're a blockchain company. Consensus is a main part, as you might have heard. And especially recently, there has been a kind of interest again in BFT-style consensus protocols, which date back to the 80s or even 70s in the distributed computing world, because of proof-of-stake blockchains, such as Cardano, which is the one input-output is developing. And that's very good for us because we can rely on the history. We don't have to invent like more ad hoc constructions like Bitcoin, which had the so-called Nakamoto-style consensus. And in particular, if you're formalizing things in type theory, you don't have to deal with probabilities, which is quite convenient. So it's very important to get this critical part of the blockchain implementation right, and ideally have formally verified implementations of those things. Right. So in the very short time I have, I cannot really go in depth for you to get a deep understanding of this protocol we're formalizing called Jolteon. But I hope to convey kind of the methodology we use in the company. And kind of more importantly, the tool of choice of Agda for this. So what are the requirements? First of all, we want a readable mechanized specification of the protocol, something that people can understand, even non-Agda experts, let's say, and has no ambiguity whatsoever. So you can really get to all the details there. These systems have some kind of properties that we would like to prove, like safety and liveness. So we want this to be mechanized proofs. And all of this to somehow be able to be computed or help us in the actual implementation of things. So we don't just want a symbolic exercise, but something that you can extract executables out of. And finally, because actually formally verifying the full implementation is unrealistic, we want some kind of conformance testing with an actual implementation, connecting the formal and the real thing. And we've been doing it actually for quite a long time in the company. James Chapman started back in 2019 mechanizing the operational semantics of Bluetooth, the smart contract language. I myself have spent a good part of my academic life in the ledger model of Cardano called extended UTXO and formalizing properties about it. It's meta theory essentially. And most recently, we've shifted our focus to the consensus layer of blockchain. And we've already talked about it in last year's types and published a full paper this year about a simplistic academic such protocol called Streamlit. So if you really want an in-depth look on this, please look at this last paper. So consensus is kind of operates in an adversarial kind of context, but not that adversarial. Maybe this painting by Hieronymus Bosch is a bit too dark. So it's kind of, you have some adversaries, but at least 2/3 of those participants are honest. They have honest behavior. Otherwise, the protocol doesn't work at all. So I will just give you a bird's eye view of how we would model such a system. We have two layers, the global one. This is common to any protocol we've actually verified, which takes care of the messaging, kind of the simplistic network assumptions we make. And then there is a local layer, which is the actual thing you would implement. A node running would be the local behavior of each one of those nodes. So how do we model this? It will be a transition system between states that hold some information. In the global setting, it's the current time, all the individual local states that we'll have, and we'll see in a minute. A network buffer which keeps in transit messages that have not been delivered yet. And the history. This is kind of the ghost state, you could think. It's not necessary, but it really helps to understand things. And then the transition system is described by an inductive relation that describes how how you can transition from state to state. On the left, we have the generic messaging advancing time part, delivering from the network buffer to individual inboxes in the replicas. Advancing time has to be constrained somehow because we're assuming a partially synchronous network. So a message has to be delivered within some bound big delta. And then on the right, we see like deferring the rest of the specification to the local semantics. We'll see in a minute. Most importantly, these are parameterized or they inherit some properties from the global system, like which is the process that I'm actually specifying now, what is the current time, and so forth. And crucially, they can emit messages optionally to be sent to other participants. Now, for dishonest participants, there is no notion of state. We don't keep track of what they actually do. We don't know anything about them. Just the fact, the only observable kind of action in our model would be that we receive messages from them, which can be arbitrary, apart from the fact that they cannot impersonate the honest participants. Or in other words, they cannot forge signatures of the other participants. And that's all there is to it. This is a common specification, kind of the BFT layer. This is how every BFT style consensus protocol should start with. And the essence of the protocol is the local view. This is where each protocol has different choices. The local state, for example, keeps track of some protocol-specific things. I won't explain them here. The current round, the execution proceeds in rounds, some quorum certificates, timeout certificates, like protocol-specific things. And of course, this messaging layer I talked about, you have some inbox, kind of akin to the actor model. You receive messages in your inbox, you haven't processed them yet. Once you process them, you move them to your internal database. Think of it as a knowledge database. And eventually, the whole point of the system is to agree on a final value. In the case of blockchains, is the final blockchain you think as a replica that will never change. And the correctness of a consensus protocol is that this final field there is a consensus across all final fields. There will be no diverging opinions on that. And again, the behavior is specified as an inductive relation. I won't go into the details, I don't have time, but there is a leader in each round. They propose a block. Other people register this proposal based on some conditions that this proposal is valid, for example. Then people vote for this block. Once you have a quorum of votes on this block and some other conditions, you can finalize something. You can finalize the chain that we're talking about. And you cannot, there are many of those rules, around 20, 10 to 20 rules. And you cannot really arbitrarily use these rules. You have to follow some sequential logic to it, go through some phases in a predetermined way. Surprisingly, the original Jolteon paper does not even have this diagram, which is like the first 5 minutes of studying this protocol, you have to write it down. And this is kind of the first step. This is the readable specification. I hope it is readable, which is already useful. You can stop here. You can give it to people as documentation, reference documentation. It's unambiguous. It's type checked. There are no type errors. There are no typos, and so forth. Next step is to actually prove the safety condition at all. There are no diverging opinions. Think of this as doing the meta theory in a PL setting. So we take traces of those steps by taking the reflexive transitive closure, and we consider reachable states from the initial state. Then safety is merely this statement that says for any reachable state, if there are two blocks in two different replicas final field, one is the extension of another, or if you think in terms of blockchains, one is the prefix of another. And that's quite an involved proof on paper. We closely follow the structure of the original proof. So we would have to prove the main lemmas that the paper describes, such as unique certification. At each round, if people have voted enough for two different blocks, then they are the same. And this is a very common argument also in the Streamlit protocol we had done before. We saw the same lemma, the same exact proof technique based on quorum intersection, basically. 2/3 and 2/3 have a common participant. It's like a very simple reasoning. Now, the interesting part, and this is common to anything I formalized in my life, really, you read the paper, everything is nice, you can describe them. To actually prove everything in full detail, you realize that this is just 5%. It's kind of the tip of the iceberg in all the things. And you eventually need to prove tens or even hundreds of lemmas, depending on the complexity of the thing. So one such example is that a very simple invariant of the system, at any point in time, the local database is reflected in history. I never forgot in my rules to update the whole history. And the proof is like very simple rule induction. It holds at the initial state, every possible step preserves it, and so on and so forth. So this is how you build up like all these invariants. And now this gives you much more power than the first step. We're at the end of the second step, because you know the protocol makes sense, first of all. So you should go and implement it. And all those properties we've identified, almost 100 of them, can act as guidance for, say, a property-based setup where the implementers test, hopefully using quick check or something of this sort, these properties. So you gain a lot even at this point. But I promised you computability, right? And I only showed you relations, logical constructions. These are not something you can immediately run. Although some of the update functions could be extracted and used, but this is kind of minor. What we really want is decidability proofs for all our logical constructions. Hopefully, Jan talked to me about, had this previous talk about decidability. I don't have to introduce it. We have decidability of basic type formers. Most of our logical statements use these type formers, and only a handful really need some search problem. You have to manually write some piece of code, but this is not terribly difficult. And there is a nice benefit that you get proof by computation. You can write example traces without giving the actual proofs. You just write a state using those rules without giving manually the proofs for everything, which is useful even before proving safety, just to make sure you have some unit test, basically. So, okay, we won't go through the example, but this already gives you, these decidability proofs are something you extract to decision procedures, which are by definition sound and complete, that people can use. For example, if a proposal is valid, has to be checked by an implementation at each node. It's far better if it's a formally verified extracted code from Agda. And finally, connecting to the real thing, because so far I've just talked about this formal thing that informally guides the implementers, but there's no connection. So the final step is to basically take the rules, erase all logical artifacts out of it, and come up with a kind of labels of your data transition system, what drives the system, which you can argue whether it's a valid sequence or not, precisely when there is a proof in our step semantics, which is by construction, again, sound and complete. Also gives you an evaluator because we are in a constructive setting. And if you prove decidability of that, then the implementers can easily log order all the actions of the system in a text file or something and run a sound and complete decision procedure to tell you if you are conforming to the formal semantics. And that's all. Yeah, I hope I conveyed briefly that this is readable in a mechanized fashion, computable in terms of extracting computational content from your formalizations. And we're now working on liveness, which is significantly more difficult than safety. So if you have done such things before, come talk to me. And like the trace verifier now just gives, for example, if you are not producing valid traces, it will just give you proofs of negation, Agda, which is, you probably need something like Jan mentioned previously. You need some nice error messages, constructive negation in a way. Yeah, and that's all. Thank you.